All right, in the last week, day 20, pulse propagation. With your help, the elves managed to find the right parts and fix all the machines. Now they need to send a command to boot up the machines and get the sand flowing again. Cables connect to modules. Modules communicate using pulses, high or low. When a module sends a pulse, it sends that type of pulse for each module in its list of destination modules. Several modules, flip-flops, are on or off. Starting off, if a flip-flop module receives a high pulse, it is ignored and nothing happens. If a flip-flop receives a low pulse, it flips between on and off. If it was off, it turns on and sends a high pulse. If it was on, it turns off and sends a low pulse. A lot of rules. Single broadcaster, when it receives a pulse, it sends the same pulse to all of its destination. There's a module with a single button on it called the button module. When you push the button, a single low pulse is sent directly to the broadcaster. After pushing the button, you must wait until all pulses have been delivered and fully handled before pushing it again. Never push the button if the modules are still processing pulses. Pulses are always processed in the order they're sent. So if a pulse is sent to modules A, B, and C, and then module A processes its pulse and sends more pulses, the pulses sent to modules B and C would have to be handled first. The module configuration, here's our puzzle input. Lists each module. The name of the module is preceded by a symbol identifying its type, if any. The name is then followed by an arrow and a list of its destination modules. Sounds a little bit similar to yesterday. In this configuration, the broadcaster sends to A, B, C. Each of these is a flip-flop. A goes to B, B goes to C, C goes to INV. INV is a conjunction module, which, because it only has one input, acts like an inverter. Sends the opposite of the pulse type it receives back to A. By pushing the button once, the following pulses are sent. After this sequence, the flip-flop modules all end up off, so pushing the button again repeats the same sequence. Here's a more interesting example. Broadcaster, 2 flip-flops, single input module, multi-input conjunction module, untyped module named output. Push button does stuff. To get the cables warmed up, the elves have pushed the button 1,000 times. How many pulses got sent as a result, including the pulses sent by the button? In the first example, the same thing happens every time the button is pushed. 8 low pulses, 4 high pulses. So after pushing the button 1,000 times, 8,000 low, 4,000 high. Multiplying gives a number. This sounds like it's going to be cycle detection, because I imagine that this is going to be 8 bajillion in part 2. Okay. Consult the configuration, determine the number of low pulses and high pulses that would be sent after pushing the button 1,000 times, waiting for all pulses to be fully handled after each push of the button. Okay, so I guess for part 1, we can just write it to work so that we understand it. I almost can't even tell which one of these is the test input. Is this the test input? I guess we have 2 examples. So I guess let's get started. Day 20. I think we have 2 tests, so we'll go with RS test right away, and then case with our input. What's the answer for this one? And then what's the second one? Not that. This. And then case with input, string slice, case, expected, also string slice, process input, expected. Looks like we have a problem. Maybe it's the comma? Yeah. What's the number for the second one? Okay. 2 test cases. Very much likely neither working. Cool. Cargo watch X next test. Got our tests running. So what? Broadcaster, arrow can have something in it. It could not have something in it. Got to build a set of little computers effectively. Conjunctions are going to have memory. What is the arrow? Oh, this isn't. Okay, never mind. This is just an arrow. So we've got broadcaster, flip-flop. What are we calling that? Inverter, converter. I guess this is the name of it, and this is what it sends to. And then we just need to define the behavior for them. Conjunction is the one. So flip-flop, conjunction, broadcaster, each have names. What are we going to have? I guess we're going to have a hash map of some kind from string slice, because that's the ID, to, I guess, machine. And I guess for the machine, we've either got broadcast, flip-flop, or what was it? Converter, conjunction? Conjunction. Broadcast has a vec of destinations. Flip-flop to start out has, I guess, also a vec of destinations. Are these all vec of destinations? Flip-flop has potentially 2 outputs. Can everything have a multi-input conjunction module and an untyped module named output for testing purposes? So a pulse is sent to A, B, and C, then module A processes its pulse and sends more pulses. The pulses sent to B and C would have to be handled first. So I guess we have an inbox for everything. And I guess we have a signal, right? Because it's either high or low. Conjunction also vec of signal, say the output for broadcast. And then I guess these all have output, right? And it does seem like they can all be a vec at least. Let's check our input. Here's an ampersand with a bunch of outputs, and here's a percent with a bunch of outputs. So anything can split. I guess technically this is a graph where each node holds some state. I think knowing what order to traverse the graph or run our algorithm in is going to be the big thing. So let's start with getting these in, I guess. So broadcast then. Broadcaster is just broadcaster and some outputs. So we get rid of the broadcaster on the front, and then we do separated list 1, tag, comma, space, alpha 1. So this parser will only succeed in the case where there's a broadcaster on the front. So we're going to do OK, input, and then machine, broadcast, outputs. This is not supposed to be a hash map at this point. This is just a machine. So machines is going to be many 1, or rather separated list 1, line ending alt, where the first one is broadcast. The second one is flip-flop, and the third one is conjunction, where those two need to be written still. So flip-flop is going to start with a percent, or not a percent. Yeah, a percent, right? Yeah, percent. And then the name is going to be alpha 1 on the input. We're going to ignore a tag of space, arrow, space, I think, before we do the separated list, which is the outputs, which should just work. Then conjunction is going to be the ampersand with the same setup, right? Name, outputs. So we want to keep the ID around, I guess. So we keep the string slice that is the ID around for every machine. I'm just going to write that in for broadcaster because it's always going to be broadcaster. For this, it's going to be name. And for this, it's also going to be name. So we need that hash map now. Machines into iter, map, machine, machine.id, comma, machine, collect, drop it into the response, make sure that we get our tuple going. Machine.id probably needs to be no field ID on machine. Oh, right. Do we have these all return tuples? So the reason that's true is because each of these is an enum. It could be a struct. They all have outputs. They all have IDs. So we could make this machine type and have this be a machine, and we'll snake the ID and the output because all of them have that. Drop that in here. And then machine type will be a machine type, which I don't know that we need anything for broadcast. We don't need ID and we don't need output here, which means that type doesn't need that anymore. So we've got an ID and output and a machine type, and now they all need to be reworked just a little bit like that. So now we return machines that are machine types, or have machine types anyway. This is flip-flop with an empty inbox, conjunction with an empty inbox. I think these inboxes are going to be necessary. It's possible they don't. So let input machines equals parse input, expect, should parse, debug machines, and then to do. Machines doesn't have debug, so we need to go implement that. So we have 2 examples here now, right? This should be the first one. Broadcaster goes to ABC, A goes to B, flip-flop type, C goes to inv, flip-flop type, inv goes to A, conjunction type, B goes to C, flip-flop type. That's good for that one. I assume that means we're good for the other one too. A splits at inv and con and is a flip-flop. Inv goes to B and is a conjunction. Con is a conjunction and goes to output. Broadcaster goes to A, B goes to con and is a flip-flop. Okay, so we have everything, we're good. Now we need to think about how we're actually going to do this and what the logic needs to be. So broadcast sends, flip-flops sends, conjunction sends. Conjunction needs some memory. So flip-flop modules are either on or off, so we need some state. So for flip-flop, it is either, we'll give it a status, and status is either going to be on or off. If a flip-flop receives a high pulse, it is ignored. If it receives a low pulse, it flips. So if it was off, it turns on and sends a high. If it was on, it turns off and sends a low. So what do we have to do that? Do we implement machine here? The ordering of these really feels weird a little bit. I feel like these inboxes need to be global. So maybe process gives back a vec of signal and destinations, and that would be self. Flip-flop is missing status. Flip-flop is missing status, so we'll add that in there. For our to-do in here. So we'll keep this as process that returns a vec of signals and destinations. I guess technically this could do something to like a hash map or whatever. I feel like I want to be able to implement something on flip-flop for like how it should process a single signal. If flip-flop receives a low pulse, all right, maybe we just start writing the loop and then we'll figure it out later. Flip-flops are off initially. We did that. Conjunctions. Conjunction module first updates its memory for that input. What does that mean? Okay, so it needs conjunction modules. Remember the type of the most recent pulse received from each of their connected input modules. They initially default to remembering a low pulse for each input, but the conjunctions don't know what their inputs are just from parsing, so we're going to have to fill them in. Yep. So we match on machine type. If it's broadcast, we do nothing. If it's a flip-flop, I don't think we need to do anything. If it's a conjunction, or I guess, let's do it this way. Let's do map, machines.iter.map, ID and machine, and we want the IDs of machines that are conjunctions. So I guess we don't really need to match here, but we do need to filter map, or this is some, this is none, none. I guess this is just matches, right? Iter, filter map, collect. These are conjunctions. Stop debugging that out. We get conjunctions inv and con, and then inv. So inv for this one is the only conjunction, and inv and con are here. So then we need to find the inputs that produce for a conjunction, right? Because for each input, we need to bootstrap a conjunction with its appropriate, I guess, hash map of memory. So conjunction up here is actually a hash map. That's from string slice to signal, I guess. And this brings our lifetime back into machine type, which needs to get passed down from machine. And this needs to be defaulted, but we could just set it up anyway. Right? Hash map new gives us an empty hash map. The fields here don't matter, so we're just going to put ... here, just to be clear about that fact. And then with the conjunctions, we need to figure out which other machines are going to output to that. I bet this is going to be a flat map. I think that's true because it could theoretically do what this is doing. And we need to cover the case in which machine A outputs to both of these. I guess we don't really need to flat map it. What is wrong with machines.iter? Syntax. Machines. Oh, let something. I don't know what that is yet, so I'm just going to name it T. This is ID machine. I guess this could be a fold now that I think about it. Is this going to be a vec? This feels like a hash map. Or what? String slice to vec of string slices. And then we need to use turbofish syntax for this to get the new one. And then for C in conjunctions, if machine output contains C, then act entry C dot and modify push ID or insert vec with ID. ACC needs to be mutable. So basically, if the machine output that we're going over contains the conjunction that we're looking for in the output, then that goes into a hash map. If it already has an entry in the hash map, we push that ID in. If not, we insert a new vec with that ID. And then at the end here, we should have a hash map from machine ID to, we'll call this inputs. And then for input and inputs, which is key and value, this is going to be conjunction. This is going to be inputs, input machines, machines.entry conjunction, and modify machine, which is a machine, mutable access to a machine, match machine. Well, let's do let machine type. Wow, that did 0 for me on autocomplete. That's unfortunate. Memory ... because we only care about memory, equals machine type, else unreachable has to exist. Memory equals, and what are these? This is a vec of strings that we have for the input machines. We need to do input machines .iter or into iter, I guess. It doesn't really matter. Map ID signal low, collect. And then we have probably mutability issues. This needs to be mutable to start with. Cannot assign twice to a mutable variable. That's because this needs to be mutable. And then hash map string slice signal cannot be built from string slice signal. So we dereference that. And then our machines debug should come out with memory C low for inv. And then where's our other one? Oh, this is only inv, right? So for inv, it's only C for this one, starts low. Inv and con. So inv is A, that's true. And then con should be A and B, true. So we've got our memory set up. That can probably be bit storage if we want to optimize that later. So we have memory now. If it remembers high pulses for all inputs, it sends a low pulse. Otherwise, it sends a high pulse. So do we assume everything in the inbox is local, is like relative? Or because there's like a process function here, right? Like conjunction needs to accept a bunch of inputs and apply them to the memory. Flip-flops need to accept a single pulse and pulse out. And we need to run everything after. So I feel like that's just batches, right? I feel like instead of having inboxes here, right? Like these inboxes don't need to exist because I think we're going to store this globally, which would mean what? We have to push the button at some point. So pushing the button is for 0 dot dot. I'll call this button pushes, and I'm just going to do one button push for the moment. So for 0 dot dot button pushes, machines dot get broadcaster unwrap because we know it exists dot output. This is kind of the thing where I want to have a process function, like give me the things that you are supposed to, like I guess we do let inbox equals vec, right? Why is there, oh, because it's not labeled. And inbox is going to be what, like signal string slice? I guess this isn't a vec then, right? Because we have to send a signal each place. So this is a hash map of string slice signal. I feel like it's a vec of those though. We'll see. So our inbox is empty, and this inbox probably needs to sit up here. No, it doesn't, because this inbox needs to be cleared on each button push, I think. But the machine is stateful, or like the machines are stateful. So we get the broadcaster, we unwrap. I guess that's our inbox though, right? What do we send for the broadcast? How do we know what broadcast is pulsing? Is the button always a low pulse? When you push the button, a single low pulse is sent directly to the broadcaster. Okay. Also, pulses needs to be 0 here. So this starts off as broadcaster low, and then in the inbox, we need to like take ownership because that's all we're going to do. And then for pulse in is where to send it and what to send. Machine.get, I guess ID signal. Machine.get ID.unwrap because it has to exist. .process signal. Machines.get unwrap process. Process doesn't exist, I think. No, process is this. So if we match on machine type here, then we say that broadcast is going to give us the same signal we got. So this needs to be a signal. So I guess machine type broadcast needs to return like self.output.iter.map. And this is going to allocate memory, and I'm going to be okay with that because I still don't know how much effort this is going to take overall. And this is going to have to be that, and process is going to take that. We're going to match on that, and then this is going to have copy, which is fine. This is a very lightweight structure. So then process for broadcast just gives us back the signals that we need to send to the next stuff. It is probably more allocation than we need to do, but that's what I'm going to do. I guess we could return the pulse count too, right? Pulses plus equals output.length means if we send 3 pulses from the broadcast, then we get 3 pulses logged in. So we log them when we send them. And then the output needs to get thrown back into this inbox somehow. I guess we build up a new inbox from the hash map. Hash map feels like the wrong structure for this right now, but we're going to go with it. Because I don't think we send multiple pulses. So if we create new inbox in the same vein as old inbox, I think these need to be vecs because I think they're going to double up. And I think this is the right way to batch them. They're processed in the order they're sent. I guess this could just be an ever expanding vec then, right? So it doesn't even need to be a hash map. This can literally be a vec of tuple. And then we don't necessarily need new inbox because this can be mutable. And then what? While inbox.pop. Is pop the right thing? A vec deck is probably what we want here. So what? Pop back. I'll let some ID signal equal index pop back. Then we do that and we get rid of the for loop. So that means we do extend with output. Extend signal string slice is not implemented for vec decks. Oh, I have the order wrong here. Let's keep the ordering of our tuples correct or right between process and the other stuff. So let's do ID signal for our, and extend is mutable. So we're good there, I believe. And then this will just keep going. And then for each button push, yada, yada, do the thing. This should now be crashing on something else. 48, that's perfect. So I guess we start pulses at 1 because we're going to send to the broadcaster, and then the broadcaster is going to send. Because technically every time this loop runs, we're snagging the broadcaster with a signal. So that's our button push. So I guess pulses plus equals 1 here then. So now we just need to determine how to process, right? Right now, process is taking a shared reference to self, but I think we want a mutable reference. So for flip-flop, let's do that first, because conjunction is going to be a little bit harder. Probably not too much harder. So if it receives a high pulse, it's ignored and nothing happens. So in a flip-flop, I guess we match signal. For high, we do nothing. We're going to return a vec here. I'm not going to worry about the allocation. I can fix it later. For signal low, we need to do some stuff. We need to, it flips. If it was off, it turns on, sends high. If it was on, it turns off and sends low. So this does need to be mutable self. So maybe we match on both of them here, signal and status. And then if it's high, we do that. If it is low and on, we do something. If it is low and off, we do something else. There's something wrong here with my braces. I think I have one too many. Yeah, that was it. So if we're on, then we need to be off. What do we have here? Can't borrow is mutable. Can't borrow is mutable with a shared reference. That's process, right? Machines get, I think this is get mute for us. Status off is an issue because expected mute status found status. Yeah, okay. Dereference, and we have an issue because used after move because we're ref muting this. Do shared reference on the match, which will mean that we are effectively like referencing that and then do the mutable later. And then same thing, right? Status equals status on, and then we need to send a low pulse to our outputs. So if it was off, if it's turning on, send a high pulse. And if it's turning off, send a low pulse. So we need to do this here and here. My auto formatter is not working. Yay. Just move all that to the right there. And then this is not going to be this signal. It is going to be signal low because we turned off, right? And signal, oh, that is the type signature. And then signal high. So we've got our flip-flop. Flip-flop should be running. And then we've got memory. Conjunction modules remember the type of the most recent pulse delivered for each of their connected input modules. They initially default to remembering a low pulse for each input. When a pulse is received, the conjunction module first updates its memory, then it checks. So got memory dot entry, I guess. Entry ID is the thing. Back of string slice, we process, we've got self and a signal, self. Oh, we need where it came from for memory. If. I don't think we're giving where it came from. So process actually needs to take in the sender ID. So this process is not just signal, it is ID and signal. And then process needs to have its function signature updated because this is going to be sending machine ID, which we are going to use down here. Sending machine ID. This will always exist. So end modify, memory location, whatever signal this is. Explicit lifetime required in sending machine. Is that up here because of the A? That looks like it. So memory location equals signal, right? And then memory dot values dot all s equals signal high, right? I guess we could do any low too. If it's high for everything, send low. So we need this thing again. Dot then some unwrap or new signal. We need to implement equality, which is fine. And then that all works. And this needs to be new signal, assuming we got that logic right. And then equality doesn't exist on signal. So we need to go do that. And these are probably not referenced appropriately. Okay, so not yet implemented. We're added to do on 219. We debug pulses is 8. Is that true? Oh, we need to debug all the pulses, don't we? In the first example, same thing happens every time a button is pushed. 8 low pulses and 4 high pulses are sent. So first of all, we're not keeping all the pulses. Second of all, we need to do high pulses and low pulses. I guess this starts out with low pulses, right? Because every button push is a low pulse. And then we need to debug out the right thing here. High pulses and low pulses. And then output.iter. I guess for output underscore signal equals output.iter. I guess for signal in. Get my syntax correct here. For signal in, match signal, signal high low. Says high pulses plus equals 1 for every one of them. We're just going to count them all. It's fine. Low pulses plus equals 1. Unexpected closing delimiter. Probably this. Yeah. Okay. So we're getting 4 high and 4 low, which means they're not counting enough. So while let, are we popping correctly? Let's debug that. Broadcaster low and then starts at C. Let's do this instead. Let's do info, ID signal. Guess these are all individual, right? 1, 2, 3, 4, 5, 6, 7, 8. I guess that is fine. We don't really need tracing here. I think my issue is just that I'm not popping off the right side here. Maybe not. Debug output here. So we broadcast low, and then we get immediately 3 lows. So we have 4 lows already. And then we process A low, and we get B high, which should get pushed back onto the stack. We get B low, which is our original from the other one, C high. So we've got a B and a C still to process. We've got C low, inv high, and then B high doesn't get an output because it's a flip-flop. C high doesn't get an output. Inv high sends A high. Inv high sends A high, is that right? Inv is a conjunction, right? Let's debug the conjunction memory because I think that's our issue. Pull in tracing. Let's do it. Let's get our tracing going. Then swap everything over to info. Run only one of the tests. Part 1 tests, test, process, case 1. And then we get the issue that signal doesn't implement value. And we actually need the bug output for a bunch of this stuff. That's all fine. 3 skipped tests? That's not right. Did I get this wrong? Part 1 tests, test, process, case underscore 1? I got the name wrong there. Part 1 tests, test, process. Oh, I had one semicolon or colon. Okay, so let's also get info happening there. So now we see everything. Let's get rid of the input because we don't need to see all that input because we're only running one test case anyway. So let's chop it there so that we see everything on the new line. Okay, output, process, output. Do we have a list that is supposed to happen here? Here's our list. Let's pull this. So button low to broadcaster, broadcaster low to ABC, A high to B, B high to C, C high to inv, B runs next. Is that supposed to happen? B does nothing. It's just not represented in here. C does nothing, also not represented. Inv goes high and inv is high and goes low to C. No, goes high to A. You know what I didn't do? I didn't instrument the process. So our log format here wants the send, from, and to. Can we output that? Let's do something a little bit more similar to that for our output format here. Let's do, this is ID and signal. Let's do ID arrow for the output because this is ID sending that to those. So we end up with broadcaster outputting low to these. A outputs high to B. B outputs high to C. C outputs high to env. Nothing, nothing. Inv outputs high to A. That's the problem right there. And that's because inv gets a signal. The inv is getting high, which I think is correct from earlier. And we go in and we thought we were getting what? Is that inv? Are we getting the wrong ID here? Because we've got memory C low and C should be sending high to inv. So we're not keeping track. This is just where it's going, not where it's coming from. This ID is where it's coming from to that output, but we need where it's coming from here, I guess. So we process ID and signal and we're sending to output. So we could return the from there as well, because if C is sending to these outputs, then those outputs get put in and they don't remember who they got sent from, but who they got sent from is actually very important for us. So let's do something here. Let's do type from is a string slice, type to is a string slice, add our lifetimes in there. And then when we're doing this in process for the machine, I thought we were getting the sending machine ID, but we're not. So this is actually all fine. We don't need to change that. We just need to change our storage up a bit. And I think we also need to change these. So these are all 2 right now, but we want from as well. We want the sending machine ID and the ID. And the issue with that is what? It's an issue in all places. Expected tuple with 2, found 3, because this now also has to be from to, and this is from. We want this to be from to. I don't know that we need to keep this in all of them, but for the moment we're going to. Sending machine ID, ID looks good there. And then down in our process here, for this, we're going to have from and to, and all of the currents are 2s. So this is going to be from, And when we process, we want to pass in from instead of ID. And then the vec deck, this is button, right? From button to broadcaster. Machines get mute ID. Is there an issue with machines now? Machines was mutably borrowed here in a previous iteration of the loop. Oh, explicit lifetimes needed here. This is going to be A. The vec. Okay, so now we're getting B sending output, and button is just sticking around, and button doesn't need to stick around. So this from gets sent in here. We're now sending this in as a capital S string, which I guess we were borrowing from here before. So process from is a capital S string. We send that in. It comes back from button to broadcaster, from button to broadcaster. So we get the broadcaster, we process on the broadcaster, change that to M. Machine process, give it where it's coming from, which is button, get back the output, which gives us from, to, and signal. So it's got to be from broadcaster, right? Next one has to be from broadcaster. So from button, sending a signal. We've got the sending machine ID, which is not what we want here, I guess. This is the original sending machine ID. These are the outputs. So this does need to be ID. Unwrap on a none on 83. We've got memory C low. ID is the ID of the machine. Output is A. Sending machine ID for the current needs to be C, if I remember correctly. So really what this is then is this sending machine ID shouldn't be passed through, because when we, not when we memory, we have ID here, right? Self machine type, so self.id. So that should be self.id, right? All of these should be self.id, not sending machine ID. Then high pulses 4, low pulses 8. Is that correct? High pulses 4, low pulses 8. That is true. So 1,000 times and then multiply them. And I'll pull that capital S string. I changed the from and to capital S string because I was trying to debug a lifetimes issue, but I think the lifetimes issue was actually that I shouldn't have been using this sending machine ID at all, at least not returning it anywhere, and I was returning it. So I think we'll be able to take that out later. Let me clean that up a little bit. So if we go down to our high pulses, low pulses, right? Then we are, okay, high pulses times low pulses, right? Do string, because that's our output. And then this needs to run 1,000 times. So let's get our loop back in here. And then let's run this for 1,000 times. And then our test passes. So let's try to pass our other test as well. One passed, one failed. So let's snag, this is 4 times. I guess that's 1,000 for each, right? So we should be getting 4,250 and 2,750. What do we get? Unwrap on a none value. Okay. At 245. So here. So get mute ID. So ID signal, right? ID out. Oh, we don't have output. That's why. I don't know why output is in here. Okay. Do we need output? Is output actually going to be in, like, you know, output's not in here. So let's just nix output from here. But we can't get rid of output in that input, right? We're still unwrapping on a none value on 245. That's con, because con goes to output, but we don't have an output. That's really annoying. I think I'm just going to ignore this case. And then our test is passing. Yeah, okay, fine. We need to hold this case in, I guess. Do we have, I guess, an output that doesn't exist as an input here? Instead of doing it like this, let's do, we have the machines, right? Machines.iter.fold vec accumulator next. And this is those two vecs and the next machine key to deal with. So ID and machine. So let's push IDs into vec1 and let's extend vec2 with the outputs. Type annotations needed. I think that's correct. I think double string slice and regular string slice. I don't want to run, I want to test. And I'm just going to debug this for the moment. And really what I think I want is to check the hash set of these two. And it should just be broadcaster. Let's stick this in a random closure or a random block so that this doesn't get contaminated with anything else. AB equals this. Hash set from A because we need to bring it in. Difference hash set from B. Expected hash set, found hash set. Let's do this to get these values the same. I'm losing it. Hash set. Okay, so we got t.difference t2. We're just going to debug this out. conf b broadcaster A output. I guess difference isn't really what we want, is it? Values that are in self but not in other. So really what we want is T2 difference T1, because we want, I guess T1 is not it, T, because we want to look at what's in the output that isn't in the input. And there's nothing in the first one. The diff for case 2 is nothing. Is that true? Okay, so that's not it. It's something else. So I think we can be reasonably certain that the real output doesn't have this, but this does produce the error that we were panicking on. So we do actually have to run it. So we'll panic here and then go through it, I suppose. The other alternatives to unwrap or empty vec here, which unfortunately passes the second test. Both tests pass in that case. That's not good. So I don't know what that is. I don't know why we have to unwrap or empty, but that was part 1. Okay, well, that's really unsatisfying. So the final machine responsible for moving sand down the island has a module attached named RX. The machine turns on when a single low pulse is sent to RX. Reset all modules to their default states, waiting for all pulses to be fully handled after each button press. What is the fewest number of button presses required to deliver a single low pulse to the module named RX? And my guess is that if we just run this, it will not complete. But what would be the signal if we were doing it that way? There's only one RX here, so we need to call RX, which means that we need to have LB. So RX is going to come out of output, and it will be the only. The question is, do we include that or not? I think we do include that. If we come up with that, we still have to run it. We can't just chop off immediately. So the low pulse has to be handled, which means that when we pop here, if RX break, well, let's copy this into part 2 first, run that, take that out of part 1 so it still works. And then I don't think this is going to work. There's no way that's the right answer. Yeah, too low. There's no way that's even close, right? It's not that easy. It's not going to run that fast. Do we need to fully process that first? Does it need to be here? I think that gives the same number, right? Which is the wrong number. Okay, it's got to be a single low pulse though. It can't just be any pulse. So ID equals RX and signal equals signal low, right? So if we run that, then it should run forever. Very different number. Also stopped. Still too low. It's a higher number, but it's still too low. RX doesn't process, so it's not like we're going to get another signal from it. Okay, it doesn't matter if we break here or we set a should break, let everything try to process through till the end and then break. It seems that the low signal to RS is the last one. There's no way putting out all these logs is a great idea, but there it is. So it's gotta be cycles. I think my implementation here is wrong in some way because it stops. I'm dumping out the log output, but like it stops, which I don't think it should stop. I don't think it's supposed to do that, but like my day 20 part 1 tests both passed. So I don't know. Something's wrong, but it doesn't affect the test runs, I guess. We have to get to RX, which means that we have to LB. LB, there aren't that many inputs, right? But there are 4 that go into LB. FK, BR, RZ, and LF. So let's start with this one. Oh, it's the fewest number of button presses. It's not the same calculation even. Low pulses and high pulses. It's button presses. So the number isn't even what I want. Part 2, this doesn't even matter. When we break here, we actually need I. So debug I. Save, assuming that everything's going to break on a button press. Let's not test part 1. I guess let's not log that out. But if we do that and we debug that, then we get no output. Oh, you know what the problem is? This is infinite. That's the problem. This is supposed to just run. Oh. So if we cancel that and we look for a different one, what is it? FK was one of them. Does this stop? That stops at this. So where's our, here we go. That stops at this. BR stops at this. Negative, whatever. We're going to call that an overflow, I guess. BRRZ and LF. So all of them are odd, hopefully co-prime in some way, which is something Advent of Code really likes. So can we do an LCM of this? Grab this number, dump it in here, try to delete the commas, and submit. And that is the right answer. That, I can't. Oh, that is so lucky. I want to at least code that in. I don't like that at all. I don't like this at all. Okay, so button pushes is out, and I guess num breaks equals 0. Let LCMS equals vec. We're not going to count the pulses. Let num break. I guess num breaks is LCMs. It's the same thing. I don't think it matters if we do it up here or down there. I think we'll do the test up here though. We don't need should break. We don't need the high pulses or the low pulses. Get rid of this. Get rid of this. That's going to be some LCM calculation like the other day. We can get rid of that hash set calculation we did earlier. Where's the hash set stuff? This little weird diffy thing. So single low pulse to RX. Final node is RX. Machines.iter. I guess filter. What is it? ID machine. So if machine.output.contains final node, I guess that's it, right? And we'll filter map this, then some ID collect, let I don't know, penultimate nodes. Let's go fancy. Let's go penultimate nodes. Contains final node, then some collect. What is this? A vec of string slices? What's wrong with that? Oh, it's doubles. Take a reference off. Take a reference off the top. All right. Penultimate nodes needs to be 4. Let's do a debug with penultimate nodes and then a panic just to make sure that we're getting the 4 that we think we would. We do need to deal with this. This is going to be, I don't know, not U32s, but it doesn't matter. I'm just getting the compiler working. Penultimate nodes is just LB. This is a find map that gives us the 1 that we unwrap because it has to exist. And this one isn't looking for the final node, the penultimate node. Is that how that worked out? Is that what we just did? I can't even remember. It's been 2 seconds. RX. And then we need to do the calculation for LB. So penultimate node, penultimate nodes, debug. This should give us 4. FK, LF, BR, RZ. Totally good. We're going to roll with that. This is broadcast stuff. This is input stuff. This is, I don't even remember. LCMs are going to have to be pushed in. If LCMs equals 4, break, and then machines get mute map. Once everything is set up, this little function here is not too bad. Machines get mute map, whatever. Where's the test? There's the test. I guess we want mute here because we don't want to do this twice if we have to go through again. So not penultimate node. Let's do penultimate nodes. I don't know how you would do this programmatically if you didn't know ahead of time. You'd have to search for everything. That's really how Advent of Code is going this year, though. You either inspect the input and get a short answer, or you don't inspect the input and potentially never solve it. Contains ID. Is that right? Is that what we're looking for here? Expected double string slice found string. Let's not make that a double string slice. That feels weird. Go penultimate nodes. And I thought we were then summing that way already. I'm going to do both of them. Yeah, okay, that'll give us our double string slice. So if penultimate nodes contains that and the signal is low, then penultimate nodes dot position x equals ID, right? And then penultimate nodes dot remove I. This is going to make us have shared reference issues, and we're going to go option usize for that. We're going to unwrap this because we just checked to see if it existed. So we're going to get that usize. We're going to remove it, and we need to LCMs push. What is it? I. And I is usize. So LCMs are going to be usize. Also got to be mutable. Penultimate nodes also has to be mutable. It's going to be remove index, not I. LCMs push I. That should give us what we need. And then where's our LCM from the other day? Part 2, day 8. LCD sound system. So that's how it's feeling right now. So LCMs, 2 string, right? This is just okay. And pass that in like that. And then we run and we get some number that is not the right number. Why is that not the right number? Am I removing the wrong index here? Let's debug this out while we're doing it because we're getting the wrong number. And I would really like to at least, why is this an issue now? Oh, because it gets pulled into here, we loop around and then hit the next one. Okay, so FK, RZ, LF, and we hit BR first. Is that true? We do hit BR first. We should probably look at what these numbers are as well. So let's go I here, I guess. And these are one off, it looks like. 3876, 39, 10, 40, 56, 40, 56. Yeah, 40, 56, 40, 78. These are all off by 1. I don't know why they're off by 1 because it's I starting at 0. That's why it's off by 1. Push I plus 1. That's going to give us our answer. Boingo, boingo. This is the right answer, right? 8341, 250, 834. Yep, there we go. That's it. There's day 20. Up on GitHub if you want to see it. I am not happy with part 2 at all. I'm also not particularly happy with part 1, at least the way that I coded it. I feel like part 1 for me got very messy. I hit one situation in which I was passing something into in a spot that I didn't think I was passing it into. So I swapped everything to like capital S strings at one point. I don't like that. I would like to go back to references. I'll probably do that in a refactor. Overall, part 1 for the deep dive, I suppose. Well, do we have benchmarks for this? Let's do benches. Why not? So we're talking pretty long, very long, very, very long. So my iteration code is probably just slow. Heavy with allocations is my guess because I'd used all those strings. I'm using a lot of vex as well. So I'm assuming that if we run part 1 with dat heap part 1, 20, this is going to be big. Yeah. I mean, it's not as big as I thought it was going to be, but it is 7 megabytes, and I don't think that we need that much. That's quite a bit. If we do it for part 2, it's probably even worse, 31 megabytes. So we're allocating a whole ton. Some of the biggest allocation we've done, all of Advent code, which is probably slowing us down quite a bit. So the benchmarks aren't great today. I really feel like I bumbled through that, even though we did get the right answer and everything. Doesn't fill me with a whole lot of confidence today. But you know, that's how it is sometimes. I've been doing pretty good so far for so long, and I think this is just not a problem I enjoy doing, which is how it goes. There's 25 other problems to do. So let's deep dive part 1, talk about it a little bit. We've got this input here. We start with a broadcaster and we have to send out pulses for ABC into these flip-flops and into these, I can't remember the name for this, conjunctions. So I think any of these can have any number of outputs. So broadcaster can have ABC, but flip-flops can also have like BD, whatever, and conjunctions, I got it that time. Conjunctions can have multiple as well. One of the things that's really a little bit awkward about this is that when we parse this, we actually don't have enough information to build our machines. So we have to build a flip-flop machine, we have to build a broadcaster machine, and we have to build a conjunction machine. But the conjunction machines have some memory in them. And that memory is comprised of the inputs to each of those conjunctions. But until we parse the whole thing, we don't know what all the inputs are. So in our case, what I did was I did one pass to parse and one pass to set up the memory for each of the conjunctions. It might be able to be done in one pass by doing like ad hoc insertion of some kind, but I just didn't put that effort in. So what happens then is the button that we press sends a low signal to the broadcaster sends it to its outputs, and so on and so forth. So how did we do this? Part 1, we set up 2 tests. The second test is actually pretty important because this like non-existent output thing here is actually in the real input. That's the RX at the end. Not that you end up running the same part 1 in part 2 anyway, but notably for part 1, if you're going to run it like this, you have to deal with this output piece. So make sure you pass this second test is kind of what I'm getting at if you brute force part 1. Our process, of course, starts with a parse, as almost always. Our parse is nom, separated list, and then we write 3 parsers, one for broadcast, one for flip-flop, and one for conjunction. I think this is the real insight for the parser today. It's that we can write 3 separate parsers that do the whole line, right? So we write a parser that does this whole line, we write a parser that does this whole line, and we write a parser that does this whole line. And we can alternate between them, and when one fails, it'll try the next one. And they will all basically fail immediately. So broadcaster would fail on the percent, the flip-flop would fail on the broadcaster and the ampersand would fail on the percent and on the broadcaster. So these get failures very quickly, and this is one of the kind of really powerful things about parser combinators and the way nom works in general, is that we can write these parsers, which are all separate parsers for each line, and because they fail and try the next one, we can stick them all in an alt and say, try broadcast. If broadcast fails, do flip-flop. If flip-flop fails, do conjunction. And in the end, we just have this vec of machines. Because we have this vec of machines, we need to into iter and map those into our hash map, because we're going to do all of our access by key. So altogether, we end up with this machine type or machine type enum, a status of on and off, and a signal of high and low. The machine struct contains the type, which is where kind of our machine logic lives, the ID of the machine, which we really don't actually need to keep around in this struct because we put it into the hash map, but I keep it here for debugging purposes and just because it's not that expensive to keep it around. We never really clone machines or anything, so it's not like we're duplicating this data or anything. Finally, we have the outputs. The outputs are the IDs we need to send to. So this is like ABC or something like that. Each of the machine types gets either a broadcast, which we have special logic for, a flip-flop, which we have special logic for, or a conjunction. These are where we store the state for each of the machines. So a flip-flop stores a status, a conjunction stores some memory. In our case, the memory is a hash map of the input ID to a signal. And we probably could write this in a way that was a little bit more set up, if that makes sense. But I chose to just write this process function on machine. So this process function takes the sending machine ID and the signal that is being sent and produces a vec that describes what machine is sending the signal, where the signal is going, and what signal is being sent. So we match on the machine type for broadcast, the easiest version of this. We basically take the output from the broadcast, which is this vec up here, and we transform it to include the from machine, the to machine, and the signal. In this case, actually, the from machine doesn't matter, so it doesn't end up mattering. This would probably be better off as a different data structure, but it's just a little bit messy and it doesn't really affect the algorithm. The flip-flop then takes a status, and you'll see in here we're doing a lot of like ref mute and mutable references and things like that. These are just ways to make sure that we're taking mutable references when we need to and that we aren't moving things out of structs when we're matching. Because really what we need is for all of these machines to stay in that hash map and not have to move out of it or get copied out of it or anything like that. So we are effectively using all of this mutation to mutate something inside of that hash map. For the flip-flops, we set the status based on the match from the signal and the current status from the flip-flop. We use this ampersand to turn this from the mutable reference that it is into a shared reference so that we can match on it and then throw it away so that we can actually use the mutable reference later. Then we do the same output. So we could probably have a function, honestly, that generates output here. And we could abstract all three of these, or all four of these, I think I do, output generation. Also, we collect for all of these outputs, and we don't necessarily need to. So the flip-flop status is a reference into the hash maps machine, and we're just setting the status in there. For conjunction, we grab the memory, we get that as mutable, and we set it to the signal that we're given. So that is where we use which machine is sending, right? So if A is sending, then we store this signal in the A slot in the memory, which is a hash map for the conjunction machine, and then we do our processing. In this case, it's memory.values. We check to see if all of them are high. If they are, then we send low. Otherwise, we send high, and we do the same output generation. This is the core of our logic. Everything else is just making sure we run that function over and over. So we do 4 button pushes. We set our low pulses. We set our high pulses. We need to keep track of each of these individually for part 1. So every time we send a button pulse, which is every time we loop here, we increment low pulses. We do a while loop on this inbox, which is a vecdec, which I am adding to the back of and popping off the front of consistently. So that's how we're getting this kind of like infinite processing. I have this queue here. Every time we get output from that process function, we take that output, we make sure we count all of the signals, and then we extend inbox with that output, which makes inbox bigger, which means that we keep this while let going, and we're only popping off 1 each time. So it just keeps growing. We just keep processing, and it goes and goes and goes and goes and goes. Finally, we take the high pulses and low pulses after we're all done, and we multiply them and we get our number. For part 2, we actually didn't solve it using code. I mean, we kind of did, but we kind of didn't. So we kind of took what we did, and we took some knowledge from the fact that a lot of the problems that look like they are cycles for Advent of Code this year are relying heavily on LCM. And we kind of took a shot in the dark and said that this was going to be cycles. And if it's going to be cycles, and they tell us that we have to stop at a specific node, and that this is going to run forever or years or something if we try to run it brute force, then we can go in here, we can look for that node. There's only one node that points to it, but that node has 4. 1, 2, 3, 4 at the bottom. If we look at the broadcaster, that also has 4. So basically, this is an educated guess based on the fact that we're doing a lot of LCM, based on the fact that there are 4 inputs and 4 outputs, that there are cycles here, and that there happen to be 4 of them. I don't like this answer. But it does seem to be the truth. It does seem to be what works. So what we did is we put in some panics and we broke out whenever we met one of those earlier nodes, right? We set in FK, BR, RZ, and LF, and we saw when those ended, and we used those numbers, and we plugged those into an online LCM calculator, and we got our number. After that, we went back in and wrote code that will do it automatically. So the final node is RX. We grab that LB before it. We grab the 4 that are connected to LB, and we put those in as penultimate nodes, which means that when we do our loop down here, aside from deleting a bunch of code that was tracking all the signals, we keep this LCM svec up here. And every time we see this ID be one of those penultimate nodes and the signal being low, we remove that one from the nodes and we push the index +1 into this LCMs. And when all of those are done, we have a check right at the top. If we have 4, then we're done. Then we run LCM on that and it just works. So overall, we got there in the end. I'm not happy about it, but we did. So I guess if you see a cycles problem in the next 5 days, try LCM. Have a great rest of your day, and I'll see you in the next one.